Hi and welcome to this course on the evaluation of AI system. My name is Fabio and I'm going to work with you through this set of lectures. In lesson 1, we're going to see why Eval in AI system is actually a little bit different from Eval in traditional software. And this lesson, just like every lesson in this course, is open to everybody, so you don't need any statistics or coding background. It goes from examples first and concepts later. It has a playground that once again is open to anybody. You don't need to write code to play with the system, and it has some deep dives. So there are going to be deep dives for whoever wants to write code, and deep dives for who wants to learn a little bit more about the statistics and the theory behind the concepts. Quality assessment and quality engineering goes way back. I think the term bugs was it's hundreds of years old. It was made popular around 1947 to an actual physical bug creating a failure. And since then, software engineering has made a lot of progress and created a lot of good principles and good practices for how to bake quality into software and how to eval software properly. And I think the interesting part is not just that we have these practices. Maybe they're not perfect, but they're reasonably, I would say, mature by now. It's also the fact that pretty much everybody in a software company is more or less aware of these practices. So there is a kind of shared understanding, shared knowledge, and shared, let's say, language for how to talk about quality in software. And this provides us with a good base, but it's also very tricky because eval in AI is fundamentally different. So if we bring the practices we learned from the past to AI, maybe in some cases they can help, but as we're going to see already today, there are actually places where they can hurt. So we need to be a bit careful when we use the term eval, because we tend to use the same term, sometimes with the same meaning. But in AI, eval means a very different thing, as we are going to see in a few slides. So I stole this slide from Andrej Karpathy and I modified it a little bit. And what Andrej shows in this slide is this loop of the AI creating software, helping us as a teammate to create software, and us as human doing the evaluation of what has been built, and then providing input to AI for the next cycle. And as AI take a bigger role in the creation of software, it becomes more and more important that we can actually assess what is built, that we can actually properly assess the AI power system that AI itself built or that humans build. Because if we get reliable metrics, if we get reliable indicators of what we need to improve and where, then we can drive AI, and for the matter, we can drive humans to actually put the effort in the right place. So with this in mind, in this course, we're going to learn, I would say basically three things. First, we're going to learn why and how AI systems are different than, let's say, traditional software. We're going to learn how we can design experiments that can give us reliable estimate about how well a system behave and where we need to actually improve the system. And third, and perhaps most importantly of all, we're going to meet a new friend. And this new friend is called uncertainty. It's something many orgs are not really comfortable with, but uncertainty is part of AI eval. It's natural, it's there. We need to learn how to recognize it, be aware of it, manage it, and also report on it. While we go through this material, there are a couple of quotes that I really, really love, and I would like you to really keep them in mind throughout the course. One is this one by Chris Pitch. He mentioned this during his intro to probability for computer scientists at Stanford. And he makes this very good point. He says, those who are able to represent what they do not know make better decisions. And that's part of what we're going to learn in this course is how to represent what we do not know and what we do know about the system. And then there is this other fantastic quote. I think we should really keep it in mind all the time. It's a quote by Walter Lewin, a professor at MIT. And this says, any measurement without knowledge of the uncertainty is meaningless. And he says this not at a random place. He says this in the first class of the first course of physics. So it's like really important. And he says meaningless. He doesn't say it's a good first step. It doesn't say, crawl, walk, run. It's a good engineering approximation. It says meaningless. So anytime you present a measurement, you need to have an idea about how sure you are about that number. If you don't have a clue about the uncertainty surrounding that measurement, then that measurement really doesn't carry any usefulness, let's say. He goes on to say, I'm not sure why, I want to hear this at 3 a.m. tonight. I don't know why he thought that students would wake up at 3 a.m. thinking about this, but that's just to underscore how important this actually is. So let's see why and how AI systems are different than traditional software. And throughout this course, I'm going to steal one more slide from Andrzej Karpati and one more terminology. He uses this term software 1.0, 2.0, 3.0. Broadly speaking, software 1.0 refers to software as we are used to from the past. Software 2.0, the way I interpret it in this course, is essentially machine learning model trained on data. So it's the training of the weights of machine learning models. And software 3.0 is what most of us mean today when they talk about AI, which is essentially large language model and other generative AI model that we program through, let's say, prompting. So let's take one example of software 1.0. This is a simple problem. We are given a deviation of the CPU usage, a deviation about the memory usage from a computer. So we're given two numbers between 0 and 1, and we compute a general indicator that shows the anomaly about the CPU and memory usage for a given machine. In this case, is the hypotenuse of the right triangle where the sides are the CPU deviation and the memory deviation. So it's a simple function, and basically the function takes these two numbers. It checks that the numbers are between 0 and 1. If they're not between 0 and 1, it returns a value error. And then if the numbers are between 0 and 1, then it computes this factor, which is the hypotenuse of this right triangle. So it's a very simple function. And what's interesting for us now is how we test these kind of functions. And the idea behind our testing is that we try to pick data points. We try to pick example inputs that are supposed to stress the different scenario that this function may have to deal with. So in this case, we may pick 1 or 2 points that are, let's say, normal with value between 0 and 1, like the 2 points you see in the center of the square. We may pick points on the edge because we want to see how our function behave when one of the parameters is 0 or is 1. And then we may pick this point, which are marked with the X here, which are values which are not, let's say, legal, not allowed, and for which we are supposed the function to return a value error. So for example, value of CPU deviation below 0 or greater than 1. And the assumption we have is when we test these points, if our function is successful and respond correctly to these points, the assumption we make is that our function is going to behave, most likely is going to behave correctly in the entire space. So for the entire possible set of value for the inputs. And the idea is that the space is more or less continuous, and really there is no reason for why, if our function behaves well in these 2 points, for example, in the middle of the square, we really cannot imagine any reason for why it wouldn't respond correctly in other points inside the square. And because of this knowledge, we tend to believe that if the function behaves correctly on this 7 or 8 or 10 test points, then it's going to behave correctly for any input. So let's begin to see why machine learning eval is a little bit different. And we're going to take the example here of a machine learning classifier and use them as a base to make our point. And we're going to use a couple of simple examples. One example is a machine learning system that categorizes tickets. So it takes a customer support request and tries to find which category the request belongs so that they can be routed to the right team. And for this, we're going to use a public data set, which is btext. It's available on Hugging Face. And the second example we're going to use is sentiment classification. In this case, it's a movie review data set. And the idea is to have a machine learning model that takes in input this review and then tries to classify the sentiment as positive and negative. And you may see how this system can be used. So for example, if we're in a customer support scenario, we may want to classify the sentiment because maybe we want to answer to a customer that, let's say, express a negative, let's say, sentiment towards our product or service. So first of all, it's important to understand, why do we need AI? Why do we need machine learning for this kind of problem, for this kind of system? Right? And we often use machine learning to solve problems that are too difficult for us to write by hand. And also because in some cases, we really are not able to write the logic by hand. So what we do, instead of coding the function that, for example, classify customer support requests or identify sentiment, what we do is we take a function that has many parameters, hundreds, thousands, millions, trillions of parameters. We initialize this parameter more or less randomly. So at the start, the function is going to give us, random classifications or random sentiments. We train this function with hundreds, thousands, or billions of examples of data inputs and of the correct output. And based on the example, we turn the knobs, we tune the parameter of this function so that on the training data set, on the examples that we give it, our function will guess the class correctly or will guess the sentiment correctly. Let's see actually how this works. If you follow this link, you're going to go to our playground. So when you get to the website, you see a screen like this. You click on the bottom one, you go to the playground. We want to go to the AI Eval playground, and we are in lesson 1. So when we get to this page, we see a couple of data set, and we can look at the data we have. So this is a sample of the customer support request data set. And here we assume we have the true label, the true class for this data set. And here we can get basically some statistics about how many data points are in each class. If you click on the ML classifier, you get to see how the ML system behave. And what we're doing here is we pretend we have taken 50 data points. We have labeled them manually with the correct class. So we took 50 customer support requests. We have labeled them with the right class. And then we apply our machine learning classifier to this data set, and we see how often the machine learning classifier gets it correct. And we call this metric the accuracy of our classifier. For this example, for this 50, the accuracy is 84%. We also can see on the right this little thing, which is called the confusion matrix. So matrix, which is for customer support requests that are in a given class, how often we misclassify them, and what we misclassify them into. So a perfect classifier will get all the items on the diagonal, but here we see that, for example, for delivery support requests, sometimes we misclassify them as refund support request. And when we speak about a specific class, for example, account, we can also talk about metrics such as precision and recall. So precision is when we say that something, a customer support request, is of the account type. How often is that correct? And this is actually 100%. And we can talk about recall. So if the true class is account, how often we actually recognize those customer support requests as being of the account type. And we can see that here recall is around 76%. So there are several account requests that we misclassify as delivery, as order, or as refund. You actually can also try to, write your own sentence and have the model classify. And if you put your own sentence in, the model will guess which probability it believes to be of which class, right? And basically, when we classify, we pick the one with the highest probability, and we basically declare it to be of that type. Right? The other aspect, which I really want to point your attention to, is this one. So when we write a sentence, what happens is that the computer actually, tries to transform this sentence into zeros and ones, because the computer only understands zeros and ones. So it tries to actually map the input sentence into a hyperspace of several dimensions, right? And here I'm just pretending I'm swashing this hyperspace of hundreds or thousands of dimensions into a b-dimensional space. So basically, I've taken all the examples we have here, and the input are mapped to a point in hyperspace, and here I'm just squashing them into a b-dimensional space, right? And that's our sentence that we just wrote. And what we see here are examples of input sentences, again, transform into this space. And what we see here is that in some parts of the space, for some sentences, we tend to classify them correctly. These are the green spots. But for some other parts of the space, we classify the sentence wrongly. So we classify them incorrectly, right? And we can see this for this data set. We can also go to our other data set. The space is going to look a little bit different, but you see that there are points that are green parts of the space for which we get our classification correct, and part of the space for which we get it wrong. We can then go to the sampling section of our playground. And what we see in the sampling section is we can pretend to pick, in this case, 50 customer support requests. And let's assume that we label them by hand. So we define and write down what the correct category is for this request. And we then apply our machine learning classifier. And in this case, for example, we can see that we are correct on 84% of the point. And we can see that if, again, we map the points into the space, for some part of the space, the points are green, which means we classify customer support requests correctly, and for some other part, they're red, which means we get them wrong, right? And we can also change the sample size. So we can, for example, go from 50 to 10 or 50 to 100. And as we change the sample size, as we draw other samples, we can get, different numbers. If we draw a larger sample, maybe we get a different set of points, a different value for the accuracy. And in the playground, you can pretend to have samples of different sizes and to have the machine learning classifier work on it and give you the output. And what I think is interesting here is that um, what we wish we had is something like this. So what we wish we had is we wish we knew for every possible customer support request, we wish we knew whether our machine learning classifier would be correct and would be wrong. And if we know this, and we take a customer dataset, we can then know what is the accuracy going to be for our classifier on that dataset and for any dataset for that matter. But we don't have this. All we have is we pick a sample. In this case, we decided to label the sample by hand. So we pick a bunch of customer support requests. We label them by hand. So we have the true class, and then we apply our machine learning classifier to check whether the classifier is correct or not. And this is all we have. So we have a space, we have a bunch of points, and if we want to be rigorous, all that we can really say is that on some part of the space, the classifier gets it right. For some other kind of customer support request, the classifier gets it wrong, the points are red. And for the remaining part of the space, we have no idea, right? So we are in a very different situation from where we were with our simple Python function, because back then what we said here is we pick the points wisely, and we can do this as a simple space without a space. And if we pick them right, we can more or less infer that if our function behaves correctly on this point, it's going to behave correctly on the entire space, right? But for our case, we don't have this. We have only a sample, we have some points, and the true performance of the classifier can be closer to the one on the left. So the classifier is awesome, the accuracy is high, and maybe in our sample we got a little bit unlucky and we got some difficult cases where our classifier gets it wrong. Maybe we get a medium classifier like the one in the middle, or maybe our true performance of our classifier is like the one on the right. So our classifier is actually pretty bad, and we were just lucky in our sample. We got easy one, on which our classifier got it mostly correct. So what can we say? Support we need to go to our boss and report on the quality of the system. We have sampled a bunch of points. We have a bunch of data, and we compute the accuracy. And this comes out to 78%, for example, in this case. Is this what we're going to report? And are we going to stand behind this number? Are we going to vouch for it? Are we going to say that yes, if we go to production with the system, we are confident that our customers will experience this accuracy if they use our system? So what can we say about our system? To find out what we can say, let's first make 3 big assumptions. We're going to remove them later, but for now they're just going to simplify things for us. The first is, let's assume that this 50, 100, 1000, whatever data points we took to sample and we manually classified by hand. Let's assume that these data points somehow resemble the distribution, the kind of real customer support requests we're going to find in production. Let's also assume that we have never assessed our model before on this dataset. So it's the first time we test a classifier, any classifier on our dataset. And let's also assume that when we manually label the data, we did so correctly. These are big assumptions. They are, to be honest, rarely true, but for now, let's pretend that they are. So with these assumptions in mind, there are actually things that we can say. So in this case, in the example where we have only 50 data points and 39 of them, the classifier is correct and on the rest is wrong. So we have an accuracy of 78%. What we actually can say is that it's very likely that our customers are going to experience an accuracy that is between 64 and 87%. It's a wide interval, but that's what science says. We can also make other claim. So we can say how confident we are that our customers are going to see at least an accuracy of 70% or 80% or 90%, right? So in this slide, for example, we say that with these numbers, we are reasonably confident, we are 88% sure that a customer in production will see an accuracy that is greater than 70%. So if that happened to be our threshold, then we are 88% sure that we are actually going to meet this threshold. So if you go to the section of our playground that is called reporting, you can see how we can report about our system. And here we say this simple form. In this form, we write down the number of correct predictions that our model make, the number of wrong prediction. And at the bottom, you can see a band, a credibility interval. Essentially, the interval where we believe the true accuracy is going to be. And as you see above, we can also see other statements that we can make based on this sample, like what's our belief that our accuracy is going to be greater than a certain percentage. So we can set a percentage with a little slider, with a little menu item over there, and then we can get the belief that our probability is greater than a certain, that our accuracy is greater than a certain value. If we add more samples, as you can see, the interval will shrink, and you can see below in bold the belief, the range of values where our belief is. It's gonna be a little bit smaller because with more data, our uncertainty about the true accuracy of the system becomes smaller. As you can see here, our uncertainty also becomes smaller when we have a more accurate model. So the accuracy of the model actually has an impact about the uncertainty that we have about our system. And there is one more point that I would like to make, which I think is really important. And when we test traditional software, we have our set of test cases, our points in the space that we test for. And when we change the function, when we change our code, we actually want to see if the quality remained the same on the points that we used to get right before. And so we ran a new round of testing with the previous data set, and that gives us the, let's say, some more confidence that we have not introduced new bugs or new deficiencies with the new software. Now, the interesting part is that in machine learning, the approach to quote-unquote regression is fundamentally different. So if we have a model and we keep working on the model and we keep minting new versions of the model, if we keep doing so and we keep testing the model on our sample data set, it may be that we actually find out a better model. So it may be that the model that performs best on our sample is actually a model that performs best when we ship it to our customer, or it may not be the case. It may be that we pick a model that somehow by chance performs well on our dataset, but doesn't perform well when we ship it to production for our customer. And that can happen, and the fact that our model performs better on the sample is just telling us that the model performs better on the sample. It doesn't necessarily let us make a statement on how well the model generalizes. And there is one important point that I think it's important to keep in mind. It may be that the model that performs better on our sample is actually also better in general, right? But what is also very likely to happen is that if we try multiple models on the same data set, and what you see here in the slide is an example where we try 12 equally good models, so models with the same true accuracy. We try 12 versions of them on our dataset. And if we pick the best, we believe that the quality of this model in this specific example is 93%. So if we have a portfolio of models, if we keep working on models, and if we keep the same test set, and we just pick which version of the model performs best on the same test set, the more we try, the more we test, the more is likely that the winner that we pick may not be the winner. And we are also, in addition, fairly confident that the accuracy that we report on the sample is not going to be what we get in production. So if we test multiple versions of a model, multiple quote-unquote improvements on the same sample, we are likely to overestimate the quality of our model. So given all that we said, how do we report on the accuracy of our model? I think one thing to keep in mind is we never report just the number. Depending on the audience, we can put the, let's say, interval, like you see here on the top right, where we believe the accuracy of the model is going to fall. We may communicate the probability that, let's say, the interval in which we are 90 or 95% confident that the accuracy is going to be in. Or like, for example, how sure we are that the accuracy is going to be greater than 90% or 70% or 99%, right? Or maybe we can actually report the bare numbers if the audience can digest that. But I think the important message here is we never report just the numbers, just the bare numbers. And this point was also made by Anthropic actually a few years ago in a post that was a little bit ridiculed on the internet. But I think it's actually very interesting that this point needs to be made. I'm not sure necessarily that adding error bars is always the right thing, because error bars can be misinterpreted and can mean different things to different people. So there is a risk that they are misunderstood, but I would definitely make sure that we never report just a number, and we say information about what is our belief about the true performance and the true quality of our model. So in summary, we have made quite a journey here. We have taken a system, we have defined what is the system under test. In this case, it's our classifier. We have defined the metric, and we pick the accuracy in this case, and maybe also precision or recall. That's the metric we decided to use to measure our system. We chose a representative data set that we believe is representative of our world that we're going to encounter, and then we pick a sample of it, and we label it. We label it with what we believe the true accuracy is going to be. There are other approaches that don't require labeling by human. We'll see later LLM as a judge, but for now, let's assume that somehow we label the example with a true label. We run our little eval workflow. In this case, it's simply running a classifier over the sample. We get the score from the classifier. In this case, the comparison with the truth is easy. We just see whether the class is the same or the class is different, and then we define how to report. It's a lot of steps that we are doing, and this is for testing one model on one data set. And it's important to keep in mind that we're going to see throughout this course, every single one of the steps may introduce a little bit of bias, a little bit of noise, and may increase the uncertainty about the quantity that we're actually measuring. So what we have seen today is essentially a difference between traditional software, where we kind of think we know the space and we know how to sample points that represent the space, and machine learning system, where this notion of sampling the space and extrapolating or generalizing to a larger space is much more difficult and much more tricky to achieve. We have also seen that in summary, this means that we need to design carefully experiment to understand how our system behave in this space. These experimentations have many dimensions we can play with, and today we have seen one of these dimensions, which is the number of samples that we get, and we have seen how the samples can actually introduce a notion of sampling noise, and how we can use calculator to understand the extent of this noise and the uncertainty essentially that this noise generates. And we have seen ways to report this uncertainty. So with this, we thank you very much for listening, and we hope to see you for lesson 2.